Okay, so I've got the given marked, I've got definition of angle bisector, and I just did that because, we've done this before. It's like, I just want to harvest anything that's obviously going to follow straight from the given. Down here, I'm going to need Q is congruent to S. I can kind of tell at the beginning that, my suspicion in this unit is that that's CPCTC, and it comes from congruent triangles right before that. A triangle with Q that goes with a triangle that has an S in it. Looking at this diagram, it's not super hard to figure out what the two triangles are because there's just two triangles. Also, now looking at the triangle, I can even tell that P goes with P because of the way this angle bisector thing looks. So let's just go ahead and say this is going to be QP, SP, R, and R, like that. What's left here then, I guess, is just to figure out, okay, which exact rule is it of the 5? I've already got those angles marked. I've got those sides marked. I've got a side, I've got an angle, so this is going to be either AAS or ASA or AAS. Okay, looking at what's there, it's not hard to figure out, I hope, that we just have a missing side here by reflexive. So let me just fill this out. Reflexive tells me that PR is congruent to PR. I could either leave it like this, or I could put the segments on and that's totally fine. And we have our proof. Done. Okay, but again, if you're going to say SAS, just let me reiterate this, make sure I say this enough. If you're going to say SAS as a reason, that means there has to be a side and an angle and a side somewhere up here prior to that in the proof. And I do. I have a side here, I have an angle here, and I have a side here. That's just one thing you might want to check before you, finish your proof or before you use one of these kind of rules. Those things have to be there before you can kind of move on or kind of be sure that it's done. Okay, this is a different section in the book. We're done with talking about triangles congruent for today, I guess, for new rules. This is about stuff that has to do with isosceles. So first of all, there's some pretty silly terms that have to do with isosceles. If you have an isosceles triangle, the first thing we know about isosceles triangles is they have two congruent sides. Okay, those are called the legs, which is bad because, we've already used the term leg today, and it had to do with right triangles, and this isn't the same thing at all, really. Anyway, they call them legs. The good news is we hardly ever refer to the leg of an isosceles triangle. The thing we refer to in an isosceles triangle the most is the base, and that's the side that we don't know if it's congruent to the other sides or not. It's the one that's not already been called congruent. And that's important because we often refer to these things called the base angles, angle 2 and angle 3. And that's what this whole theorem is about. It's about base angles. The other thing that's really a dumb term for this is the vertex angle, is this thing here. Well, remember when we first defined triangles in the first place, like any old triangle? It was defined to have 3 corners, and those were called the vertices. Each one is called a vertex. Now it's important because this one in an isosceles triangle is called the vertex. So if you use the vertex, then all of a sudden it's an isosceles triangle. I don't know. Again, that's not a huge deal. The biggest part of this whole thing is actually base angles. So the fact that we're calling these base angles is probably the biggest news of the day. And that's part of the fun of this thing. Okay, so what is it? And this has kind of come up before, but now we're letting the cat out of the bag, just kind of like the 180 in the triangle. If two sides of a triangle are congruent, so basically if a triangle is isosceles, then the angles opposite those, angle 1 and angle 2, are congruent. Maybe you knew about that. That's fine. Now we can use it in a theorem or use it in a proof. The other thing is, if the angles are congruent, then we know the sides opposite them are congruent. So that's great. What's nice about that is the original and the converse are both true, so we call it a biconditional in the theorem sheet. We just call it ITB. So if you're ever converting between two angles being congruent and two sides being congruent in an isosceles triangle, you just call it ITB. Isosceles triangle biconditional, or isosceles triangle base angles. That could stand for either thing, and that's what that's about. It's very helpful, and we're going to use it quite a bit. It's almost like whenever you see right triangles, you're kind of suspicious that maybe HL is going to be a thing, but it doesn't have to be. Whenever you see an isosceles triangle, you're going to be kind of suspicious that ITB is going to be a thing. Doesn't have to be, but it's, that's the thing that's just reserved for isosceles triangles, so there's a good chance that that's on the horizon. Okay, we've seen this kind of relationship probably too much. This is almost kind of silly now, hey, guess what? These two things have identical tick marks, so guess what? They're equal. So yeah, we're going to do this, and we find out that y is 2. Okay, big deal. The more important thing here is if you had an isosceles triangle with a vertex angle of 80, you automatically know what both of those things have to be. If the whole thing has to add up to 180, those two things together have to add up to 100, and you know they're equal, so both these things are 50. So 6x plus 8 is 50, 6x is 42, and x is 7, and we're good to go. Okay. There's a corollary to this. There are two corollaries to this, actually. Corollaries we talked about recently. Corollaries are like obvious attachments, kind of obvious like follow-ons that come from any theorem. And this one is if, we know that stuff about ITV, we know stuff about isosceles. Well, we can apply that to equilateral because our definition of isosceles includes equilateral. But what's special about equilateral is it's isosceles kind of any way you spin it. So if these two angles are congruent, that means that those two sides are congruent, then these two angles are congruent. And that also means if these two sides are congruent, then those two angles are congruent, and etc. And if you keep spinning that around with transitive, you find out pretty quickly that all three of the angles have to be congruent. Well, then the next one says, well, if all three of the angles are congruent, we've already just said recently that the sum has to be 180, so if they're all congruent, they must be 60. These aren't so important in proofs. We honestly don't see these in proofs very often, but we see them in, these complicated, calculation questions where you have all these crazy triangles in the same problem, and all of a sudden you find out that thing's perpendicular, you find out that thing is equilateral. It's like, oh, then I automatically know all these are 60, and it helps you solve the rest of the problem. So it's more helpful for that stuff, usually, just generally speaking. It's more helpful for that than it will be for a proof. But if you ever had to name it in a proof, they are on the theorem sheet and they have names. Okay, great. So if these two sides are congruent, that means the angles opposite them are congruent, meaning this thing down here has to be 2x. Well, now the thing's equilateral. Equiangular, equilateral, and so all those angles have to be 60. That's no big deal. Here's the first time we've had to solve a quadratic. If this is equilateral, right, then all these are the same, and that's equal to 12. Okay, so let's talk about this. First of all, I trust you remember this from 8th grade, or whenever it was you figured this stuff out, that this is going to be 6 and 2. I think it's a plus 2 and a minus 6. Yep, that works. I'm not going to teach you how to do that. You've already learned how to do that. I'll help you know if you've done it right or not. Anyway, that's how that works. Sometimes these things in geometry are going to factor. Sometimes you got to pull out the quadratic equation. Like our job is to kind of keep your keep your algebra fresh. So that's a thing. Anyway, this leads to the fact that y either has to be -2 or 6. Okay, we've never really been faced with this before in geometry, multiple solutions. So, and this is a little bit different than algebra. We have to be sure that any angle measure or any side length has to end up being a positive measure. Algebra didn't care about that. The domain of algebra questions was just kind of like all real numbers. Well, now if it's an angle or if it's a side, it at least has to be positive. There's some other restrictions we'll deal with later, but for now, let's just deal with that. Positive length. So it's okay if a value of a variable might be negative, so long as it makes sense in the geometry. So what if y is 6? Well, if y is 6, then this thing is going to be 12. If y is -2, y equals -2, what happens to this thing? Well, it turns out it's positive 12. So both of these numbers, -2 and 6, both make this thing equal 12, which they should, because that's what we started with. Anyway, they both make it equal 12, so they are both valid solutions, so you have to have both of these things in your answer for full credit if this is on a quiz. Okay. All right, this isn't in your notes. I wish this was in your notes. This is a great proof. And let's just go through this. Okay, given this stuff. Can we mark stuff? Well, it's kind of hard to mark x, y, and x, z, so I'm going to do that just so I can see it as I go through this proof. And, oh, you know what? I am going to write it here just because. Let's do this. Okay. X, y equals x, z. And midpoint stuff. I'm just going to say midpoint stuff. Kind of here. Okay, one way I could do this. Oh, and we're trying to prove QY is congruent to WZ. That's probably going to be CP, CTC. That's probably going to come from triangle QY something is congruent to triangle WZ something. Okay, what's interesting about that is triangle QY something could kind of go either way. Oh, that's cool. Could kind of go that way or it could go that way, right? We could be talking about triangle QYZ being congruent to WZY like that. Or we could be talking about QYX being congruent to WZX like that, right? We could kind of overlap these either way. It's kind of difficult no matter which way you do it. I'm going to use X just because this has to do with a shared reflexive angle if I do it by X. And we haven't seen many of those examples. Honestly, it's the same number of steps and it's the same kind of difficulty either way. But I just want to show the X way just because it's less like what we've already done. Okay, here's one way to do this. All right, we know W and Q are midpoints. So right away, that's congruent to that. I mean, we'd have to write this out and justify it. That's congruent to that, and this is congruent to this, which is great. But since the whole thing is congruent to the whole thing, just with a couple algebra steps, I could get that all four of those are congruent. Those algebra steps are kind of tedious. Yeah, and really, since I'm going to go with the X way to do this, the only ones I really need are those two. So let me do this in a certain way here. The definition of midpoint is that is that XW is half of XY. That's the definition. The theorem about midpoints is that XW equals WY. Since we start out with this step that XY equals XZ, I think it's actually going to be easier to do the definition. So let's use definition of midpoint. Let's say XW equals half of XY. And let's say that XQ equals half of XZ. Oh, I didn't say given. I didn't say, okay, and then this is definition of midpoint. Why is that better? Well, because I already know something about XY and XZ. I know those are equal. But now it'd be really great if I could say half of XY is equal to half of XZ. Well, I can say that. How do I know half of XY is equal to half of XZ? Think about this. Well, I knew XY was equal to XZ. How do I know half of XY is equal to half of XZ? I just took that first step and I multiplied both sides by half. Multiplication. Technically, it's the multiplication property of equality. Okay. Now I have half of XY is equal to half of XZ, but in step 2, those things were equal to XW and XQ. So now I can say XW is equal to XQ. This is one way to get, I mean, this takes kind of a long time, but this is one way to get XW equal to XQ. XW equal to XQ is helpful for, and I said this a long time ago, that down here I was going to be talking about triangle QYX and WZX. Okay. I need those as sides, right? So now I have two sides of this triangle that are congruent. I have a side here and I have a side in the original, actually. That's a side too. I need either an angle or another side. Turns out the angle's pretty easy. If I go by reflexive to say that angle X is congruent to itself. Okay, I never said why step 4 was congruent. Step 4, that's for 5. Step 4, yeah, it was this little train. XW is congruent from step 2. XW is congruent to half of XY. Half of XY is congruent to half of XZ. Half of XZ is congruent to XQ. So they're all congruent to each other. We call that transitive. Then I have a reflexive step that completes SAS and I'm done. That's a long proof, and yeah, there's a lot of sort of semantics in these 3 steps that we haven't really seen before, so I wanted to do that. Also, we haven't really seen reflexive in a shared angle for those 2 triangles, and those 2 triangles aren't exactly obvious to see. Again, we could have done the lower 2 triangles and had it be shared side YZ, then it would have been, I guess it still would have been side, angle, side. It would have been, ooh, let me think about this. Change of color. It would have been side. That would have been just as hard to get. We could have done that side, reflexive side. Whoa, wait a second. That would have been really hard, actually. I could have done this angle by ITB or something and done SAS. Ooh, I'm glad I did it the way I did it. It was actually a lot shorter that way. Anyway, you could do it either way. and it's totally fine. That's why not everybody's proofs are the same length. That's why you shouldn't put any, you shouldn't look too closely at how many points something is worth, because different people are going to do it in different ways. I think, actually, now that I see that, I think that the shared angle way is shorter. Okay, that's great. I will see you in class, everybody.